In this video, I will go over your pre-calculus first semester final review. This video is on the free response questions that you can expect to see. The first 5 are no calculated questions, so keep that in mind. And also as I go through this, I will highlight some things that you might consider putting on your formula sheet. All right, first, graphing a piecewise. So these are our different domains. So from x is less than -3, between -3 and 0, between 0 and 3, and beyond 3. So in each of these areas, we will have a different graph. Okay, and this is a -6. Okay, so -1, y equals -1 is just a horizontal line at 1. This is a greater than or less than or equal to, so we're going to put a closed dot and then just a line going backwards. X plus 3 between -3 and 0. So x plus 3, we have a y-intercept of 3, and at 0 it's a closed dot, and then a slope of 1. So this is going to be an open dot. Okay, 3 minus x, so that has a y-intercept of 3 and a slope of -1. Okay, and you can always just plug in points. Plug in 1, you get 2. Plug in 2, you get 1. Plug in 3, you get 0. So if you're not sure how to graph it, that's always a good idea. The last one, 3x minus 6. So you can start at 3, plug that in, and figure out where it's at, or graph it like you would from like algebra 1, go to -6, then have a slope of 3. Then when you get to x equals 3, start your graph. Okay, or take 3, plug it in, that would be 9, minus 6 is 3, so that dot is there, and then proceed with a slope of 3. Okay, based on this, we're going to look at the limit as x goes to -3. This little plus means from the positive side. So here's -3. From the positive side, our graph is approaching 0. Then it just has the limit as x goes to -3. Well, since there's this jump here, since it's not going to the same place from both the left and the right, that limit does not exist. Okay, so next we have this graph, and we're going to do some different analysis. So first, end behavior. End behavior is always looking at the limit as x goes to infinity of our graph and the limit as x goes to -infinity of f of x. So if that's something that you forget, you can write that end behavior is always this. We just need to fill in the blanks for the particular equation. So in this case, as we go to infinity, as x goes to infinity, our graph is increasing without bound. So we say that's going to infinity. As we go to -infinity, it's going up to infinity. Name and classify the extrema. So the extrema are the maximums and the minimums. So there are 3 of them here. We have a maximum and 2 minimums. Okay, so this first one, -3, -3, that's the naming portion, is just identifying the coordinates. The classification, it's a minimum, but it is not the most minimum. Okay, so we call this a relative minimum or a local minimum. Okay, this one at 0, 1 is a relative maximum because there's still values on this graph that are larger. This last one over here at 3, -4 is an absolute maximum or minimum. Okay, because it is the smallest on a graph. So a graph can have multiple of all of these. It could have none of these. It just depends on what it looks like. Next, the intervals of increasing and decreasing. So as we read the graph going from the left to the right, it's whether we're going up or down. So here we're going down. here I'm going up. Think about it like driving a car. We're going downhill. We're going uphill. Okay, so we want the intervals, which is the x values. Okay, so we have increasing, decreasing. Okay, it is increasing from -3 to 0, and from 3 to infinity, or you can just say when x is greater than 3. It's decreasing from -infinity until we get to -3, and then from 0 to 3. The next problem on your free response is going to be a rational function problem, where we're going to find the points of discontinuity, vertical asymptotes, slant asymptotes, horizontal slant, if any. So let's review those rules. So this is something that you can absolutely put on your formula sheet. You might want to abbreviate some of this stuff if this you would find helpful. So points of discontinuity occur when the top and the bottom have a common factor. So the first thing you need to do is factor the top and the bottom. Find if there is a common factor. That doesn't have to be. Whatever makes that factor 0 is the x value of the coordinate. Remove it, so take out the common factor, plug the value you got here into what's left, and that is the y value of your point of discontinuity. Okay. Vertical asymptotes, after you've removed the discontinuity, is going to be any number that makes the denominator 0, okay, unless you've already removed the discontinuity. Okay, anything that makes the denominator 0 is going to have a vertical asymptote, which will be x equals whatever that number is. Horizontal is the limit as the function goes to infinity. So these limit rules you need to know for this, as well as just evaluating limits on your final. So it depends on the degree of the top and the bottom. If the degrees are the same, then the limit is the ratio of the leading coefficients. If the degree is smaller on the top than the bottom, then it goes to 0. If the numerator is bigger, though, it's going to go to infinity, which means there is no horizontal asymptote. Last case is a slant, which occurs if the numerator is exactly 1 higher than the degree of the denominator, and then you'll use polynomial long division to find that. Okay, so here we are going to factor. Okay, this numerator factors, well, to get a 2, we have a 2x and an x. To get a 3, we've got a 1 and a 3, and one of them's negative and one of them's positive. So through a little trial and error, you can arrive at 2x plus 1 and x minus 3. The denominator is x minus 1, x minus 3. Okay, so we do have a point of discontinuity. Okay, because we have a common factor on the top and the bottom. So when x minus 3 equals 0, okay, which is at x equals 3, then we remove the discontinuity. So we're left with 2x plus 1 over x minus 1. I'm going to take 3, plug it into that. So that's 6 plus 1 is 7 over 3 minus 1 is 2. So we have a point of discontinuity at 3, 7 halves. Next we look for vertical asymptotes. Okay, after you've removed the discontinuities, these are no longer a part of our equation. It's anything that makes the denominator 0. So that's going to be when x is 1. If I plug in 1, that is 0. Horizontal asymptote is the limit as we go to infinity. Well, as we go to infinity, and you can look either here or here, it doesn't matter, you'll get the same thing. The degree is the same on the top and the bottom, so it's going to be the leading coefficients there, or if I do it here, same thing, you'll get 2. So my horizontal asymptote is 2 over 1, which is 2. which means that there is no slant. There are additional examples of this in the multiple choice part. This next question, we are finding the slope of the tangent line. So remember, this is the slope of a line, and as x gets really, really close to c, we have a tangent line. So we're going to use this formula. C is whatever our x value is. So we want the limit as x goes to 1 of f of x minus f of 1 over x minus 1. Okay, well, f of x is just this, so negative 2x squared plus 3x plus 10 minus f of 1. So we need to plug 1 into our equation. So that's going to be negative 2 plus 3 plus 10. So that'll be 11. Over x minus 1. So that'll be minus 1. Okay, it's a little challenging to factor with a negative, but that's okay, because we already know what one of the factors has to be. So then you just have to figure out what I need to multiply this by to get this. So this would have to be a negative 2x, and then to get a negative 1, I'd multiply by a plus 1. And you can double check. The middle term would be a plus 1 plus 2, which gives me a plus 3. Okay, whole point of this is now I can cancel out that common factor. So we now have the limit as x goes to 1 of negative 2x plus 1, and then we plug 1 into that. That's how we evaluate a limit at a value, is just plugging it in. So negative 2 plus 1 is negative 1. So that is our slope of the tangent line at that spot. Then we want to write the equation of the line. So a nice formula to use is the point slope form. And you can take our point, which is the point 1, 11, and our slope that we just found, negative 1. And you can leave it like that. If you feel like multiplying it through, you can. Your next question and your final no calculator free response will be a graphing question. So let's review those rules. Okay, you'll use these rules on both the free response and the multiple choice. So this is, again, something that you can absolutely put on your formula sheet. Okay, for our calculations, this is our general formula, and this can be either sine or cosine. The amplitude is the absolute value of whatever A is. The period is 2 pi divided by B. Phase shift is negative C over B. So negative C over B, it's the opposite of this. And then our vertical shift will be K. So we can use that information to graph. All right, so we're going to find the amplitude, period, phase shift, and vertical shift, and then graph. So for this one, my amplitude is 2. My period is 2 pi divided by B, which is going to be 1/2. So that's 2 pi times 2 over 1, which is 4 pi. My phase shift is negative C, which is negative pi, over B, which is 1/2. So this ends up being pi times 2 over 1, or 2 pi. So it's going to be shifted to the right, 2 pi. This one is a vertical shift of 1. Okay, so on this axis, I'm going to go ahead and do my period of 4 pi, which makes this 2 pi, which makes this pi, and 3 pi. I have a vertical shift of negative 1. So this will be my midline. And an amplitude of 2. So we're going 2 above that line and 2 below that line. Okay, we're graphing a negative cosine, which starts at the minimum. So it would start here, but since this is has a phase shift of 2 pi, the minimum is going to start here. Now you can extend the graph on to get your points, or we can just backtrack to get my 5 points. Okay, this one, our amplitude is 3, the period is 2 pi over 3. We have a phase shift of negative pi over 2 over 3, which will be negative pi over 6, and a vertical shift of negative 2. So my period is 2 pi over 3, which makes this pi over 3, which makes this pi over 6. So 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2. But then we have a phase shift of negative pi over 6. So if this is positive pi over 6, this is negative pi over 6. For my y-axis, we have a vertical shift of negative 2, and an amplitude of 3. So we're going 3 above and 3 below. Okay, this one is going to start. We have a positive sine graph, which means it starts at the midline, but we're starting our graph at negative pi over 6. Then I'm going to go through my 5 points. So sine goes up, back to the midline, down to the bottom, up to the midline. Okay, your free response question that you get a calculator is an exponential function problem. So assume that the speed of a plane is given by s of t equals c e to the kt. And this is just function notation, you're not multiplying. So evaluate the constants, find c and k in the equation if the plane is flying at 400 miles an hour at time 0 and 500 miles an hour at time 40. So my c is going to be 400. It's always our initial value. So I'm going to set 500 equal to 400 e. We're solving for k. It takes 40 seconds to go from 400 to 500. Okay, so we're just algebraically going to solve this. So 500 divided by 400 is e to the 40k. We're going to take the natural log of both sides, because when I do natural log of e to the 40k, we just get 40k. And then we'll divide. Okay, and then you'll type this into your calculator, because we need a calculator for this question. Okay, so that would be the natural log of 5 over 4, close parentheses, divided by 40, gives me 0.00558. Which means my general equation is going to be s of t equals 400 e to the 0.00558 t. We're going to use that to find when it reaches the speed of sound, which is 750 miles an hour. So the math here is going to be pretty much the same, except for solving for t. So we'll divide. Take the natural log. Divide by that. So t is going to be the natural log of 75 over 40 over 0.058, which if you type that into the calculator gives you 112.654 seconds. So these are the 6 questions that you can expect on your free response.